The question is about a metallic rod, length L and rotating in a uniform magnetic field B with an angular velocity omega. L omega B is given. This is the rod and this rod is undergoing a rotation. The length of the rod is L. In this case, what will happen is the charges in a metallic rod, which are usually negative charges, electrons. The electrons in the rod are spread all across the length of the rod. Electrons are present all across the length of the rod. And as the rod rotates, the electrons experience a motion. They gather a velocity. Just as this happens, let's say there is an electron over here, a negative charge electron over here, and is moving with the rod. It is situated, let's say, at a distance of x units from this rotating end. Then its velocity will be equal to x omega. With this velocity, it is moving in a magnetic field. Now imagine the magnetic field is into the page. The magnetic field is into the page and the rod is rotating in this particular field with a velocity which is, let's say, in this direction. How do we see this? We can see that the magnetic field is into the page and the rod is rotating like this. That means the velocity of the electron is like this and the magnetic field is like this. Now you see the rod is rotating like this, so velocity will be directed this way and v cross b. And now since electron is a negative charge, v cross b, using the left hand curl rule for negative charges, let me show you one thing. If this is a negative charge, use the left hand rule. If this is a negative charge, use the left hand rule, and that means v cross b will force the electron this side. Now you see the electron will be experiencing a force on this side. And how much force is that? The force of the magnetic field Q of V cross B. Now since the velocity is perpendicular to the magnetic field, therefore the magnetic force on the charge electron is simply EVB. And that means there is a electric field that is going to get generated, and this electric field is due to the magnetic field, motion of a charge in a magnetic field, and E is equal to VB. Now this electric field will direct, or the force on the electron will direct the electron to the end of P, and that means the electrons as such will always start moving due to the force, magnetic force on it, towards the end of P, and this end P will get negatively charged. Now in a metallic rod, the charges are always, majority charge carriers are always electrons, and hence the electrons will experience a negative, a force towards the end of P. Because of this, you see, V cross B will direct them, V cross B will direct them towards the end of P. This end will have excess of electrons and this end will have deficit of electrons. So point P will get negatively charged and point Q will get positively charged. Now the thing is, this accumulation of charges will develop an electric potential along the length of the rod. And how much potential will be built? Now let's say you consider a small length of the rod. Let's say we consider a very small length of the rod. We don't need this part of the question any further, so we can have a diagram here. Now see, we have, let's say, the length of the rod taken like this, and with this end as P and this end as Q, and the magnetic field, let's say, is located like this. Now what is going to happen is, say for example, this is a small length of dx where there is a set of negative charges, the negative charges. These negative charges will have a difference of potential, dV is equal to E dot dx. and E is equal to VB, and V is equal to how much? V is equal to X omega. So therefore this dV, which is the small change in potential across this length dV, is going to be equal to E dx, means VB dx, and V is equal to X omega. So X omega B into dx. This is your dV, a small change in potential along a small length of the rod situated at a distance of x units from the rotating end. Now, integral of this dV should be equal to V, should be equal to a potential. Now potential difference delta V, this should be equal to delta V, and that will be equal to omega B integral of x dx. Now x varies from x equal to 0 till the end of q, that is at x equal to L, and therefore we are going to get this result delta V as equal to omega B into x square by 2. So therefore half of L square, and therefore half BL square omega. Option A is correct, and this 1/4 option B is incorrect. Now this point P, the end P, is negatively charged. Therefore the potential at P will be less. Therefore this option is correct. And the end P is negatively charged and end Q is positively charged only during rotation of the rod. Now this is a very particular type of a question. If rotation stops, if the rod stops rotating, omega will turn to 0. If omega turns to 0, the induced EMF turns to 0. Omega 0 means delta V 0. Delta V 0 means what? Delta V 0 means potential at this end and potential at this end are equal magnitude, are of equal magnitude. And that means only during rotation, as long as omega is non-zero. And now see, rod can rotate that side. I mean, the rod is right now rotating clockwise. The rod can rotate anti-clock. If the rod would rotate anti-clock, then what would happen? Then V cross B would push the electrons this side. So this option is a critical option. This is a very nice trap. This is a very nice trap. Listen to me again. I repeat what I say. If the rod is rotating clockwise, then using the left hand rule for the negatively charged electrons, you can say that V cross B pushes electrons to the end of P. Now what if the rod would be rotating clockwise? This option does not say the direction of rotation has not been given. You see here, the direction of rotation not given. Direction of rotation not given in this option, and hence this is a good trap. Now if the rod rotates anti-clock, in that case what is going to happen? Use the left hand again. Electron goes like this, electron is flying like this with the rod, and V cross B would push. V cross B would push the electron to this end. This end in that case would become negatively charged. So end P is negatively charged and end Q is positively charged only during clockwise rotation. Only during clockwise rotation of the rod in B field, then this option would be correct. Then if this clockwise would have been there, without this clockwise, this option is not takeable. This is not in general true and so cannot be taken. So therefore the moral of the story goes like this, that if rod rotates clockwise as is given, if the rod rotates clockwise, then the Vp value is negative and Vq value would be positive. See this. But if the rod rotates anti-clock, then what will happen? V cross B will push, V on the electron will push, V cross B will push it to the end of Q. Then VQ would turn negative, and Q would be negatively charged, and VP would be positively charged. Do you see this difference? This makes this question extremely special if we modify this as I have done. This is a peculiarity of physics by Rn. Now you see, this option is wrong in general sense, so this is not given. Now, if the rod stops rotating, then Vp equal to Vq. If the rod stops rotating, means omega equal to 0. Omega equal to 0 means induced EMF 0, delta V 0. Delta V 0 means Vp equal to Vq. So here, if rod stops, if this stops, omega equal to 0. Therefore, delta V 0. And that means this, and therefore this option is correct. And that's all about this question. See, your basics need to be absolutely smooth, butter smooth. Stay revised, stay subscribed. See you for more questions in the next question rounds. Thank you.